All right. Thank you so much for coming. My name is Daniel Mor. I'm a technical artist at Virtuos, and I like to do procedural tools and creating games. Today, we're going to talk about PCG and buildings. We'll take a short look at the results and create a similar toolset. So first, a quick video showing the results. Alright, so let's take a closer look at the buildings tool feature. In this talk, we're going to mostly focus on this one, the buildings. We're going to change the size, floors, and props here. And we're going to sort of learn procedural thinking. How can we spot patterns and use similar operations to solve them? Here are some buildings variations. So we randomize here the props, the floors, and here are some variations. Next is the city tool. We will move the city around. The tool is showing the preview mode by default. We can change parameters such as seed and size, and control the results by setting the minimum and maximum floors, for example. So we kinda control the ranges. Eventually, we will generate the actual buildings. So it's kinda a tool that contains the building tool. Let's view the materials functionality. The material itself is very basic, no textures. I'm going to share a few tricks. First, how to create the mask that we did, and the variations for actors or instances, so we can do both of them. Here we change the basic material properties, color, metallic, roughness. Modules. The modules were designed in plasticity. In Houdini, we've done UV, naming, and packed an FBX. Here you can see it in Unreal with the material we went over earlier. Grammar is a fancy way to describe patterns. In the context of building, we will set walls and floors patterns. It was added recently in Unreal 5.5. This shows a button for artists to interact with predefined wall patterns. The idea is to kinda simplify the controls wherever we can, either by using buttons, presets, or anything that is simple to do. We will now set up the project. We would prioritize logic over just connecting nodes or doing a step-by-step tutorial. I hope to deliver value for both beginners and advanced users. Building tool. So let's set it up. Start by enabling the PCG plugin, edit, plugins, PCG, and just enable it. To create assets, simply right-click in your content browser, click the blueprint class, and choose actor. Name it, and type PCG to do the same. Open the blueprint, add a PCG component, and link the PCG asset to it. Our goal now is to control the size and the amount of floors of the building. Open your blueprint and add 3 parameters: floors, size X, and size Y. They will be whole numbers, integers. We are now going to open our newly created PCG class. We're going to use the getActor property node and just read the variables by specifying its name. We basically read it from the blueprints. Next, we're going to use the create point grid node. It is used for floors and the size of the building here. We basically create 1 point per floor. With this node, we get the power to sort of precisely spawn points. It can be a 2D grid, like the name of the node, and it can also be a 3D one, or a point above another point, which is just perfect for floors here. This is how your graph should look like so far. You will notice a few more nodes. I added some math nodes, such as converting meters to centimeters. I'm not going to focus on them a lot today. We're going to keep the math pretty simple. Add, subtract, multiply, floor and modular. Here are our floors. I added a gap here between for visibility. But if you select your create grid node and press D for debug, they should appear on top of each other. Sometimes some floors can be bigger or smaller than others. We can kinda use that fact to generate more interesting buildings. So let's mess a little bit with the floor size. Since every point or cube, which I will use interchangeably here, can contain attributes, we're going to add an attribute for each floor. The first one will be shrink direction. Add a noise and round nodes. The noise will generate a 0 to 1 values. The round will ensure that we get either 0 or 1. If the attribute of that floor is 0, we're going to shrink it from the front. If it's 1, we will shrink it from the back. But direction is not really enough. How strongly do we want to shrink each floor? 40%, 60%? Another attribute can help us answer this question. It will be shrink strength. It's going to be the same idea. 0 to 1 noise, but this time we're not really going to use round at all. So a 0 would mean no shrink, and 0.5 would mean 50% shrink. We can also spice it up a little bit with some height gradient, so we can control that lower floors will shrink more or less, depending on what you want. One problem with shrinking floors is that we might get some small deviations. Usually it will look bad and unintentional. To fix that, we're going to sort of step our shrink, allowing only few specific shrink values. If we allow 3 values, 0, 50, and 100, a 60% shrink will become 50%, and 10 will become 0, meaning we don't shrink. 6 to 8 steps worked well for me, but honestly, meters per step would be more reliable. Before we continue, let's create sort of 2 mini tools. We're going to use them a lot. This one splits any cube to smaller cubes. It will measure the size of the cube and break it down accordingly. It means that this cube, let's say a 3 by 3 meters, will be sliced to 27 smaller cubes. Next, we're going to normalize float. It's another sort of subgraph. So let's say each floor has an attribute. 0 is 0 and 1 is 1, up until floor 9. We can find the maximum and minimum attributes of those floors and compress them into 0 to 1 range. So floor 0 stays at 0, floor 9 now becomes 1, and the rest of the floors are somewhere in between. So far, we just played with attributes. We didn't really do any shrinking. So let's do it by looping over each floor. In the shrink loop, each floor will be converted to 1 meter cubes with the mini tool we created earlier. The position of each row of cubes will be normalized between 0 and 1. Filter any row with lower density than the floor shrink strength. The second floor is shrinking 40% from the front. We just delete values below gray. This is our graph so far. Most of the extra stuff that I didn't mention are just extra controls for the user. For example, disable shrinking altogether or allow one direction. And there it is. We shrank the floors. They now adapt to the size of the building, and we've added control for seed, direction, strength, and steps. But first, let's do some walls and corners. We can spawn them. We're going to start by splitting the floors into first floor and other floors. The input of the node will be floors after we shrink them. The output is going to be walls and corners as modules. We are going to work with a grid of 1 meter cubes. This time, we're using a 2D grid, no need for a 3-dimensional one. We will move them around and just check if they overlap. That's about it. So to create point grid, use the create point grid again. This time, we do not want many cubes stacked vertically, just one 2D layer. For the wall, duplicate the cube grid. We're going to move it 1 meter to any side, either X or Y, and subtract from the original. Now the wall is just ready, as 1 meter cubes. For the corner, it's pretty much the same idea. We just do it twice. We take the wall, duplicate it again, and subtract. So we now get a corner piece. Here's our tool so far. The corners here are blue, and the walls are made from 1 meter cubes. It reacts to size changes. Now we're going to sort of split each wall, or rather combine those modules. Since all of them are 1 meter, and sometimes we want like 4 meter pieces, we will do it in the next slide. So the logic of the wall split is large to small. We try here 4 meters until we fail, then 2 meters until we fail again, and then we fall back to 1 meter, which we know we always have. The graph itself is looking scary, but it's pretty much the same row, duplicated 4 times. So let's dive into one row. First, to avoid errors, we will figure out if there are any points left to fit walls into. So keep the first point using attribute filter, add some attributes, we will set it to true, and then input it to the branch node. If there are no points, the branch node will interpret that as false, as it didn't really add a true attribute here. And then it will effectively stop the flow of the graph, outputting to A. If we do find points to fit walls into, filter the ones that fit using attribute reduce, modulo, and filter by range. In this part, we get the sort of remainder, the part that won't fit, and we can funnel it into the next smaller module test below. Lastly, we divide the index by the module size, floor, and partition. So let's take a look at like a 2 meter example. Indices are usually 0 and 1. We're going to divide them by 2 for 2 meters. This will yield 0 and 0.5. Flowing it will give us 0 for both 1 meter cubes. So now our indices are 0, 0, 1, 1, 2, 2. We're going to partition the cubes according to their new index, basically grouping each cube that are the same index. And this is our segmented walls. They are not 1 meter cubes anymore. They are kind of combined cubes at different sizes that we wanted. We are now ready to actually spawn some actual meshes, filter the points according to their type and dimensions, and use match and set attributes to specify which meshes to spawn, and eventually drop a static mesh spawner. But how do we actually specify which meshes do we want to spawn? We're going to create a structure, open it up, and add 2 variables, one float for the weight, and one mesh for the mesh. Add it into your blueprint just as a normal attribute, set the defaults, and eventually go to the PCG building and read it using the same node that we did earlier, getActor property. Here's our building, now with real walls and corners. You're going to notice some doors here. Let's see how it was done. Each wall segment will get a random noise. The range of the front will be 0 to 1. The sides will be 0 to 0.5. We're going to pick a module and just simply convert it to a door. It's going to be based on what's the highest number, so it will be very likely that we get some door at the front and less likely that we get a door at the sides. Here's a zoomed out view of the doors graph. And here's a video with some close-ups. We use the building circumference to determine how many doors to spawn. We can simply count how many 1 meter cubes we have. And you can look at it later in the recording to get some more details. And here are the doors, marked in green here. We expose door frequency for this and seed for the user. For example, I want a door every 20 meters. It will always spawn one door, so we kind of force it to spawn a door at the front. Our graph just became too big for a simple picture. Here's a video of it now. One type of control we want to expose is seed. It will allow us to kind of randomize the whole building by just changing a number, or randomize a specific part of it, such as roof props. Here's an example of global seed and individual seeds being added together in order to sort of determine the final seed. And here's another way to do it. I wanted to stress that mutate seed is kind of dependent on position. So we can basically change the seed by changing a little bit the position of the building. This will yield different seeds if we move them, and since our calculation is at world origin, it should be consistent unless we change it. A common issue is when you kind of move your PCG graph, but it stays at the same place, at the world center. We can simply move it to the center of the actor. We're going to use a new node, getActorData, as a single point. This will kind of give us a point where the actor centroid is, and this is where we're going to copy everything. I placed it right before spawning static meshes. It makes the graph kind of more stable. Our building moves now, and everybody is happy. Let's tackle the most important things after walls. It will be roofs. We're going to convert our floors to cubes once again, but all of them. We're going to duplicate it and move it downwards 1 meter. Finally, we're going to just remove the overlap, and we end up with those roof cubes. Here we show the graph, filtering the roof locations yielded 1 meter cubes. Now, we're going to just split it into bigger modules. Let's apply what we learned here at wall segmentation before, but this time we're going to do it for the roofs. So we're going from 1D algorithm here to 2D. We're going to start with large modules, 4 by 4 meters, and then going smaller until we reach 1 meter. Here we try 2 by 2. We got to the first 2, and then we start failing because there are just not enough cubes to satisfy it. So we fall back to 1 by 1 meters. The input of the graph are 1 meter roof grid, and the size of the module you would like to fit, let's say 4 meters or 2 meters. This is how the split graph works. We're first indexing and then splitting to valid or invalid modules. We're going to set the index of each cube in X and Y. So the cube of in the corner will be 0, 0. The one next to it will be 0 and 1. Here's a more detailed explanation. You can read it a little bit later, but the idea is that we just check how many cubes occupy each segment, and then determine if it's a valid segment or not. So a 2x2 will require 4 cubes. Now the roof is present, adapting to any changes, including the size of the building or the shrinking settings that we set. So far, we made a lot of progress. Floors, walls, doors, and more. We are now going to basically set dress our building, adding props, pillars, and floors, just to generate some areas with higher details. So if the previous section was the tutorial, this is the final boss. We're going to do wall props. The idea is to kinda avoid placing props on open areas, such as windows. We want to avoid areas that stick out beyond the wall's baseline too. This is a common problem, and usually we tackle that with tagging areas or something like that, but I wanted a fully procedural solution that kinda adapts to your modules. So we're going to scatter some points on the walls and the props. We're going to measure the distance of the props to the walls using those points. If the average distance in this case is less than 7 centimeters, the prop is determined as valid. For the main loop, we will loop over each floor. We're going to input the locations to test, the walls as points, and the props as points. And here's the full process. If the average distance is too big, we just discard the prop. We just compare those points, and if the distance is too big, just discard it. It's going to avoid windows, and it also adapts to changes of the input meshes or walls. Here's a look inside a graph where we use the distance node to compare distances. After we've done with the distance test, we apply weight, remove overlap, and add coverage attribute, with the final node being a static mesh spawner. And those are the results. Our props are not floating. We didn't have to explicitly indicate where they should avoid, and it kinda leads to interesting patterns. It's also fast. The wall props are kinda the most complex part of this tool. For now, we're going to speed up and focus more on the logic. Starting with the corner props, we're going to duplicate the corners and move them 1 meter outwards, and that's it. We're doing a very similar thing here. Move, noise, normalize, coverage and seed. Nothing new. Here are the results. We can change the corner props coverage or change the modules and their weight. Let's say we want more of a specific module, or we don't want this module at all. For the roof props, we simply scatter. If we simply scatter props on each roof, we're going to encounter overhang, like in this example. To solve it, we are going to measure each asset, and based on its biggest axis, we scale down the viable spawn locations, basically shrinking the roof according to each asset. It's going to help us avoid overhang. This graph shows how to apply the logic. We are looping over each asset, and then shrink the roof according to it. Here are the results. There's no overhang and just many possible variations. We also rotate it by 90-degree increments and make sure that there's no overlap. More on that later. For the exterior props, we are now going to play with the roof cubes and the walls cubes. We're going to just move them around and find if they intersect. The red cubes here are kinda perfect for us. They are not floating and they are close to the walls, a common place for people to place stuff. Here's a look at the graph. It's the same nodes, but different outcomes. And the results. Just one more layer of interesting stuff we've added to it. For the railing, it's going to be the same idea, but this time we're going to play around with walls and corners. Move both of them upwards and intersect. By this time, I kinda hope you start noticing a pattern. We're just moving cubes and checking for overlap. Nothing overcomplicated. And this is the graph. I've added here tall pillars too in between floors. Try to produce that logic, it's kinda fun. It starts to feel more grounded now with the railings. Seed parameters are now exposed for both the railing and the short pillars. It simply changes the model. For the foundation pillars, buildings usually float on uneven terrain. Adding a foundation pillar can sort of solve that, so they will not float and look kinda interesting. We're going to measure the distance from the corners to the ground, and then spawn pillars accordingly. Many things can be done this way. This is how it looks applied to the tool. We can apply this idea to many assets, shoot rays in different locations, and sort of create a library of smart assets that are kinda aware of their environments. The pillars here just won't spawn if they are not needed, which leads to nice behavior and optimized environments. For the ground floor, duplicate the bottom cubes, move them around, add them to the original, and just spawn tiles later. We now have the floor. It's possible to control the size, scale, tiles, and railing. This is the ground floor and foundation pillars graph. It kinda made sense to place them at the same general area. And here's the full graph. We went almost over all of it. Here are the full results of the building. Here, we randomize pretty much everything. I added a random button that kinda changes all of the variables. Seed usually can change most of the stuff, but I wanted to keep the floors stable, for example. So if the user wants 3 floors, he can still change the seed, but keep the floors. This button kinda randomize everything. Next is the city tool. We're going to go over it much faster. This is also a simpler tool than our building. To create, first create 2 assets, 1 blueprint, 1 PCG, just like we created for the buildings, but this time for the city. Add some variables. Since we want to vary the buildings within range, we're going to use a minimum and maximum scheme. So let's say a minimum of 1 floor and a maximum of 10 floors. You see those vector 2D at the bottoms, which is just 2 floats, 2 simple numbers. We will use it for minimum and maximum. So we're going to start with the same node. Read variables, create point grid. And this time we're going to move the points randomly in X and Y. We don't want them to be a perfect grid. This is the point grid before we moved it. We're going to pretty much assign attributes to each cube. Each cube will be a building according to its, will spawn a building according to its size and place. We're going to randomize the X and Y size of the buildings. We're copying the size to scale to get an accurate debug preview. And we now use the attribute normalize graph again. It is back. But this time we don't really normalize it from the 0 to 1. We normalize it to what the user wants. So let's say 0 to 9 for the floors. One issue with our approach is the overlap here. To solve that, we can use self-pruning, which I kinda love. It removes kinda overlap from everything. It's a really valuable node. Next, let's rotate each building by 90-degree steps. We're going to use the floor operation here. and just do a few simple maths to sort of get it. Here's our rotated, non-overlapping buildings. In a full city, we can think how to sort of rotate the buildings toward the road or do some more interesting layouts. We're going to randomize the possible flows. I wanted to mention that kind of real-time feedback and quick iteration speeds are really valuable. Every environment can kind of enjoy this flexibility, even just as a blockout tool. Why use the cubes for buildings and neighborhoods? We can create a blockout tool. The artist doesn't have to guess how many floors the cube is or continuously measure it and then center it like on the ground. So for the shrink strength range, we're going to randomize this one too. We're going to shrink buildings a little bit less frequently if they are taller. It kind of makes sense because we want the taller buildings to not have many variations, but on smaller buildings we want many interesting shapes. This is the guy we're randomizing. How much do we shrink? For the props, we're going to use the distance node. We will spawn less props if the buildings are kind of closer to each other. This is just a simple experiment, but you can play with whatever logic you find interesting. For the roof props, we will use regular attribute noise, resulting in more frequent coverage variations than the special noise, which is kind of consistent in space. For the doors, nothing complicated here. It's the same pattern, noise and normalized to range. We're just doing it over and over again in the CD tool, or in many other tools too. We're going to alternate between our wall types, large to small that we created, and grammar that we're going to create later. So about grammar, as I said, it's basically like patterns. It can help us achieve interesting ones, such as alternating between modules, or specifying the start and end module and end module. We're going to move the city to the actor centroid. It's a really common operation, and we've done it with the building earlier, but now just for the city. Next, we want to kind of determine the height of each building. We don't really want it to float, but we don't want it to sink on uneven terrains. To solve that, we're going to convert our building to 1 meter cubes at the base. We're going to shoot some rays toward the bottom, and then check what is the highest point that kind of snaps to the terrain. Then we're going to copy the height of the highest cube, marked in red here, for the rest of the building. Convert the base of the building to 1 meter cubes once again. Rate to the landscape, find the highest cube, and copy its height to our unmodified building. This is the only attribute we need from here. And finally, we're going to actually spawn the buildings. We will do that by spawning the blueprint actors we created for the building. So the building blueprint contains a PCG graph, and we're now using like a blueprint within and the PCG within it. We're going to override the blueprint variables, and this is why we generated all of those variables earlier. It's going to enable us full control, as if we place those buildings manually and just change some parameters. This is really valuable because after we generated many buildings, we can come and just like change one specific building. And there's the city PCG graph. Compared to our building, it's kinda light. And there's the result. We move it around and it adapts to height. We are changing the seed and the size, and the different ranges we created, such as minimum and maximum floors, or minimum and maximum size. Eventually, we generate the actual buildings. I did add here like a preview mode, which is snappy and kind of shows you how it's going to roughly look. We can even make the preview mode better by showing the shrinking presets. So let's view the material setup. Create two simple materials, color, roughness, metallic, the usual. To alternate the secondary color of some buildings, drop an actor position and round node. It's going to generate a 0 to 1 values for each actor, which might sound familiar by now. We're going to add a mask. So where would the first and second material be? The trick here is to calculate the mask at the default position of the model before we moving it or rotating it. Expanding on this idea is kinda interesting. Blend the material using the mask we created on the previous slide. And now we want to kinda add color and roughness variations to some assets. For example, AC unit will be nice if some of them were a bit more dirty or a bit darker in this example. So similar to speed tree's color variation node, but here we control the hue, saturation, and values individually. The key nodes here would be per instance random, which gets us a 0 to 1 value per piece. It's the same as the attribute noise we used in the PCG graph, but this time we're doing it in materials. Use the remap node, which is like attribute normalize, but we kinda assume a 0 to 1 inputs because we don't actually measure the darkest and the brightest pixel here. And one more thing we can do is use RGB to HSV node, which is just perfect for variations. Since we don't want to vary just the red channel or the green channel, we want to vary the hue or the saturation. This is the complete graph. And this is the material results. We're changing parameters such as colors. And we can enable per actor variations. So one of those buildings are gold tint and some is blue or red. And the per instance variations, which kind of screws the models. But it's useful for AC units. For the modules, I really enjoy plasticity. It helped me design a huge selection of models. It's a modeling software using NURBS, similar to CAD and things like that. It's intuitive to use and well designed, so if you like hard surface, I really recommend you checking it out. Here's a top view of the modules. It took several iterations to come up with the dimension and kind of make sure everything fits. But the process is satisfying. Here's a top view of the props. Each cube grid is 1 meter, so you kind of get a scale for things. In Houdini, we use to name, UV, and center the kit. We can also use Houdini to visualize anomalies like pieces with many polygons or pieces with holes. Those are marked in red here. It's very useful. For grammar. Grammar, as I said, is a way to sort of describe patterns. In this example, we're going to use it for walls and floors. It's available since 5.5. Here's the graph. We're going to start by converting a cube to a spline. Each floor will have a sort of base spline for it. We're going to use the wall extraction process we did earlier. Everything is the same, but we just take the corners and input them into a create spline node. So now we get a spline at the base of each floor. We kinda do it because Grammar expects splines as input. Starting with the vertical Grammar floors. What kind of floor pattern do we want? Do we want one first and one last floor with many middle floors in between? Or maybe we want one first floor and then alternate between different assets. Let's call them middle and last floors for this example. To the left, the grammar section was taken from Epic's example. They have a really great example in Engine. We force the direction of the spline and convert the spline to points. In the right side of the graph, we will classify each wall segment and apply different grammar depending if it's the front, sides, or back. For the horizontal grammar, it will be for the walls. I prefer readable naming over concise, so I chose wall 1M1, which is like the first module of the 1 meter dimension walls, which is a bit more accessible than what I usually see like W1 or W1A. I think it's worth the extra letters. Here we load the modules. We do that by reading the same struct from earlier. We're going to merge all of the possible wall modules. We're going to allow scale for some or all of the modules. Not allowing scale will kind of fail the segmentation process, but the scale should be really, really minor if your pieces fit. Extract mesh info is one more example by Epic, which kind of finds the dimensions of each module. Use that, it's really nice. This is the actual grammar segmentation. It's the subdivide node to the left. All of this, the grammar section will be output into this sort of redirection node. Forgot its exact name. To easily enable grammar, toggle this parameter. We're using an enum here. Enums are great because we kind of get a drop-down menus with selections that are easy to understand for the users. We could use a boolean here, but it won't be as clear as a selection, and we will lose the option to include a few more options if we want more than 2. The results are the ability to change grammar in a bit more intuitive way, either by clicking a button or editing the strings. We are now done with the project setup. I wanted to share some idea of what we can tackle next. We can explore additional city elements, roads, sidewalks, parks, and many more things that I didn't include here. We can improve the city layout. The city layout is pretty basic here. We can create spline-based buildings, ones that are not just square. Grammar is already a huge help toward it, and geometry script can generate custom-sized roofs, floors, pipes, and more on the fly. PCGX is looking awesome. It's a plugin that seems to address many of the needs for complex city layout, having more special nodes and things that can measure if they are inside of each other. Interiors can be both challenging and super interesting to tackle with PCG. And many more additional paths. Unreal 5.6 features, interactive UI, different styles, and combining it with geogeneration, pipes, and more. Final thoughts. PCG is not easy. It's sometimes simple, but can easily get complex for certain tasks. A full complex city is a significant challenge. Geometry generation is currently basic within PCG, but you can complement it with geometry script. More spline, vertex, and face operations could simplify the graphs and do certain actions more easily, like cubes to splines. PCG is super useful. Some buildings, fences, biomes, and many tools are totally viable now. PCG can also be useful for level design or gray boxing early in development. And it can also be used in the later stages to scatter points on the landscape or any mesh that we want. Filter them and then spawn meshes accordingly, such as vegetation, extra rocks, everything. PCG is also stable. It's fast, and many features I kinda expected to have were there, a lot of nodes. It supports importing and editing point clouds. So using Alembic, we can make it much more useful. Basically, deciding what do we want to spawn. We can take the point cloud and spawn additional points around it. And one more point that I wanted to say is that anybody can sell those tools in a huge marketplace, which makes it a lot more relevant now. In the future, I hope Epic keeps developing PCG. Some things I would be happy to see are animation, or in general just the ability to simulate and animate anything using PCG. Maybe even author blueprint or move characters using it. One more thing is smaller graph. I want less nodes, so let's say inline constants are coming in 5.6, which will make the graph significantly smaller. It is nice. High-level nodes, such as self-pruning or just a fence or building nodes, will be great, because one of the workflows we can do is to take those high-level nodes, break them down and change them a little bit and get another tool altogether. And advanced tutorials, it will help us explore and learn what's possible. We're done. Feel free to ask. Thank you so much. Thank you so much. Feel free to ask me questions either now or later. I will be here and in the dev lounge.
Right. So what would be your approach to add more directability in the tools? Like, say the art director wants, like, I don't want this building here, or the upper floor is too tall on this one, or the prop on that generated on the corner. Like being, you generate everything, but still have access to like the certain layers to prune and direct.
Right. So this is a really cool feature of PCG. Once we spawn those building actors, we can just click on one of them and change all of the parameters as if we just placed it manually. So we can change the floors, we can change its location or size without regenerating the whole city. So this is one approach I would go, and using splines and things like that to even have more directability.
Apologies if this was covered, I came in later, but was there any actual engine code changes involved, or was this completely...
It's 100% PCG. Houdini was used to just import the modules and sort of pack them into an FBX. It was easy because when I kind of change the modules, it automatically like picks them, center them, and export it as just one file, so I can re-import in Unreal.
Got it. And also another question is, is this being used with world partition or like without? Because we have tried using PCGs on our side, and the moment you get involved with level instances and other things might go wrong. At least it did for us.
I see. Yeah, I didn't explore world partition. I didn't check performance a lot, but I saw that it ran very quickly. So let's say still capped at 120 FPS for full HD. So for now, I didn't touch it, but yeah, it's definitely something we should explore.
Got it. Thank you.
Thank you.